All right. So the first condition, do you remember what it was? Approximately normal was one of them. I don't know if it was the first one, but
10%
approximately
10% was the third one.
normal. Now for these ones, because we want to make sure that we're assuming it's got this bell curve. This one was where we were doing the central limit theorem, where you had to test a certain amount in order for you to be able to do any calculations with it. Do you remember how big it had to be, the sample? 30 or larger. So N has to be 30 or larger. Now keep in mind, we can't do the same things that we were doing before because we're not going to have a P. Bless you. So we're not doing that NP is greater than or equal to 10 because there's not going to be that percentage in there, that proportion in there. So the only way we're going to know if something's normal is if we're sampling something that's got 30 or more, then we know it's going to resemble some type of an approximately normal curve. Or if it's normal already.
On the other one the other day, it was more than 10.
Yes, because we had this NP is greater than or equal to 10. But for this problem, these problems, we're not going to have a P. So we can't calculate those.
Okay.
Do you see what I mean?
Yes.
So if I tell you we're going to sample 12 people, a few people might say, well, it's not bigger than 30, I don't have to do any work. It is, as long as if I say, which is already normally distributed. If I tell you it's normal already, then we can assume that it's going to follow that same pattern. If I don't tell you anything about it being normal, then we got to sample more than 30 things. Or 30 things.
Central limit theorem.
Central limit theorem. Yep. So the other thing was it had to be random. So it's not like you can just go and pick 5 of your friends to do something and try to calculate the confidence interval. We're not going to be that confident if you're just looking at your friends to solve the problems for you. We want to make sure it's a random sample. And then there was another one.
10%.
Yeah, independence. And a lot of times we don't know whether they're independent. So we look for this independence rule. That means you want something 10% of the population or less. Because you want a big sample, but not too big of a sample because you might have these overlapping things and it will throw off the data. So we don't really care if we have these overlapping things or if they're independent, as long as that 10% rule is if it's the 10% rule, where it's 10% or less. So let me give you a sample problem, okay? And this is for, I'm going to put it just right here, when the standard deviation is unknown. We'll talk more about when it's known next time. But when the standard deviation is not known or the sigma is not known of the population, we might know it for the sample. We're going to call that S of x. Sample standard deviation. So we're going to calculate it with the sample standard deviation. So let's see. Do I have to write all the words to all these problems? Because you know how they're very, very elaborate. Okay, so it says the principal at a large high school claims the students spend at least 10 hours. So I'm going to abbreviate. Students spend at least 10 hours doing homework on average. Okay, and this is, said the principal, okay? That's what he thinks. To investigate the claim, an AP statistics class selected a random sample of 250 students from their school and asked them how long they spent doing homework during the last week. So they asked him how much time. From the last week. So that's, remember before we were thinking about what's a good question to ask and stuff like that? I bet that's not too bad because you might remember how much time you spent last week doing homework. The sample mean was 10.2 hours And the sample standard deviation was 4.2 hours. Let's make a 95% confidence interval. And we're going to interpret it. And it's for the mean. Now, before you throw out your Z-charts, we're not using Z-charts. Okay?
Two standard deviations.
We're using something different, okay? Let's still go through the first thing and figure out, can we still do this? We want to go through the conditions and make sure that the conditions can be met first, okay? So, let's see. Does it say that the data is normal? Because the conditions have to be, it's got to be approximately normal.
Yes. There's 250 students.
Right. So we don't know if the data is normal, but we do know there's 250 students. So we know that it's going to be approximately normal because it meets that central limit theorem. How about random? Does it say something about randomly selecting students? 10% rule. 250 students out of the high school. Oh, yeah, that was a little sketchy for this one. Oh, look at this. It says the principal at a large high school is the way it was stated in the very beginning. So let's just assume that it's a pretty large high school, okay? So that we can calculate it. Otherwise, we'll just say we can't calculate it. So I'll give you that maybe it's over 3,000 kids at this high school. Okay? Sound good? Pretty big high school. Okay. For a confidence interval, it's the same type of way, except a little bit different because we need to add in degrees of freedom, and we're using a different formula. So we still need the mean. What was the mean of the sample? So that's what we're going to use. I always sketch a little figure of a normal curve. 10.2 is going to go in the middle. What happened when someone was calculating this, a statistician back in the day, I have his name written down, I think it's Bonnet or Bonet, something like that. When he started calculating these types of calculations, he was noticing that there was more than 3 standard deviations. A lot of his calculations were more than 3 standard deviations away. So think about how many percent is normally 1 standard deviation away? 68, I think it was, right? 2 standard deviations was how much? 95. 3 standard deviations was 99.7. He was getting things beyond 3 standard deviations a lot. So he's going, there's something can't be right. So he figured out a way to manipulate it when you're doing something with means so that it would be more accurate. And it involved a T-score. A T-score. It's a lowercase t. In your book or in that packet that I print out for you every single test, you probably, you know what? I don't include it in every single test, so that's probably why. I don't include it, do I? No. Well, I'm going to have to now, right? Because, I don't know if you know, but in the back of the book are all these little sheets for you. Okay, so we've got our Z-scores over here, okay? I print these out for you, but we haven't needed the T-scores, so I don't usually print those out. Take a look at the chart for T-scores, and if you have a book, you can pull it out. It's at the very back in the tables here. We're going to need a T-score. Okay, take a look at all the components of this. DF, what do you think that stands for? Degrees of freedom, okay? You're testing how many people?
250.
250, so you need
249.
249. Okay. The other thing is, this table is kind of neat because it has some neat things in here. Notice the way it goes across up here. This is your upper tail probability. So that's kind of what we were looking for anyways. If we want to do, 95%?
Yeah.
95% confidence interval, what's going to be the upper tail here? how much percentage?
2.5.
2.5. So we need 0.025, something like that. If I try to scan down for degrees of freedom, I need to go to 249, you say?
Yeah.
Okay. So let's take a look at this. Down here, and notice even at the bottom it says confidence level, 95%. Cool. What a good check. It even has over here your Z-score for what the Z would have been at this point. So we could have probably been using that all along maybe. And then look, it's kind of spits it right out for you. Uh-huh.
Yeah,
But it's kind of confusing though because look, 95% and then it's there, but then it's 0.25 over here or 0.025. So I know it is pretty easy, but you will get this on your next ones, okay? There you go. Now, the problem is, you see 249.
No.
All right, Caleb, when you look down, it jumps from 100, then it goes to 1,000. Tell me the difference between those numbers. Can you see those numbers there?
Pretty sure that's 1,000.
It's a point.
Yes.
1.984 and 1.962.
So how's
They're pretty close, even though it goes from 100 to 1,000 from here to here. You're supposed to take the number that's smaller. So when you're in debate, you want to take always the number that's smaller within there. Okay? So instead of picking the 1,000, even if we were closer to it, we would always pick the one smaller. So 1.984. So T is 1.984. Let me zoom that guy back up again. 1.984.
No.
It's not the one that's closest to, it's the one that's lowest. Okay, it's the lower one. Even if we were looking for 999, we would use 100 versus 1,000. Okay? Always the one that's lowest down there.
Why?
So I think it's just as more accurate. It's just going to end up being more accurate. Did you know your calculator, you can actually find the exact number? Or maybe we'll figure that out after break. You can have your calculator, I know, I don't want to add more because you could just use the chart, but you can actually find the exact Z-score too. If you ever notice you're a little off on your Z-scores from the book, it's because you could actually get the exact number based on that Inspire calculator. Same thing with the T-score. So we could use like 249 if we needed to in our calculator, but I don't want to go that far just yet.
All right.
Let's hear it.
So we're asking these kids how many hours they spend. Why does it matter? Like the 250th kid that they ask, why would he have to change his answer? Like he still has the same degree of freedom. Don't understand why.
Correct. That just, I know, the degrees of freedom isn't the easiest thing to explain. I'm just trying to make sure that you get the association, it's n-1, but actually understanding it's a whole other ballgame. Okay? So I'll look into more things, but I don't want to get too, because you're going to end up with the same idea. It's one less than the total, so I don't want to take too much of your time doing that. And I was looking for a good short video that I could show, something to make it more concise, and I don't have it, but I will still look into it.
All right.
Okay? So the big idea is that we're not using a Z-score anymore, we're using a T-score for something like this. It's the same basic method for everything else. You need to find, from this formula, the formula says something like this on that sheet. Remember I said from your formula sheet, it's got sigma over radical n. We're going to be using the same type of thing, but our sample standard deviation over radical n. And then we're going to calculate this the exact same way you just did the last confidence interval.
There's way too many abbreviations for mean and standard deviation.
I know,
There's literally like 4 for each button.
But you know what? Just think of it as, when you see this, I think of standard deviation. So then when I calculated it, I thought of standard deviation was 4.2 over the square root of how many people that we were sampling. Let's hear it, Adam.
Do we know when to use T-score or Z-score?
The word mean is typically the key. Where the population standard deviation is unknown, but the mean is the key thing. Mean is T, proportion
Yeah, but the means also in Z.
was the Z.
But
When
they're
you
saying that
in
the
the
confidence
actual question